When looking into chapter 8.1, one of the first concepts that is gone over is Keplers laws. So Keplers laws come in a three. So the first Kepler's law is that planets move in ellipses. They don't move in circular patterns. If they actually moved in circular patterns according to physics, they would actually start to accelerate and they would probably not stay on path, but the most comfortable position that they have are in ellipses. Now, as we move on to second, it kind of overlaps with the first in how any planet will move in this elliptical pattern. So one of the two things that we want to focus on with this motion is the fact that as an object is in orbit around a body, this being the sun, there are two parts that we need to focus on: the aphelion and the perihelion. The aphelion is when we are furthest from the sun or from our center of orbit. A good way is that A, away. On the other side of the extreme is the perihelion. This is when we are closest to the sun. So when we are focusing on this, it's not just the distance, but it's actually the speed that we're moving at. And when we're the furthest, we're moving at a slower rate. And when we're closest, we're moving at a faster rate. So those are some of the major concepts, but here is the connection between Kepler's second law and these phenomena. If you use geometry and you use the sun as the center, and you take the same amount of time it takes from our planet per se to get from here to here and map out this area, and you take that same amount of time, no matter how much it is, usually the scientists like to use 30 days, and they map out this area, that means that everything in here, mapped out area-wise, will equal the same amount of area in here. And that's what we're talking about. Outline equal sections will have the same area. And so here, right here, is an example of what I'm talking about from month to month. And this is just another picture showing all months going forward. Now, one of the last phenomenon, which is actually where we get into some math, is where we get the formula and Kepler's third law. And it simply states right here that the ratio of the squares of the periods of any two planets that move about an object is equal to the cubic ratio of the average distance. So as we look down here, we have the ratio of the periods of any two planets or any two planetary objects orbiting. The quantity squared will equal the ratio of the distances they are from that object and quantity cubed. And you can just extrapolate this out, and this will help you with manipulation and solving for one variable, where it's the same as the period of planetary object A over the planetary object B. Both of them squared will equal the radius it is away, or the average radius is cubed, divided by the other planetary body cubed. And all you need to do is simply solve for one of the variables. And as always, I highly recommend, if you have an opportunity to choose, please choose one of the top parts of the fractions to have your unknown. And for calculators, if you have trouble putting in square roots, just remember that square root of x is x to the 1/2, and make sure you put that 1/2 in parentheses. And a cube root of x is x to the 1/3. Please be careful when putting this into your calculators, because this is where it is a little bit difficult, and we got to make sure that we use parentheses correctly. Just try to remember how we did it in class and keep on trying, and when in doubt, put extra parentheses and it should work out. All right, so that's Kepler's laws.